Hello, my future doctors, and welcome back. Chalo, let's dive into one of the most fundamental, most important topics in all of pathology. I'm telling you, this is something you're going to see every single day of your clinical life. We're talking about inflammation.
Hey, just think about it for a second. You get a little paper cut, or maybe your throat feels all scratchy. You see it becomes red, it swells up a bit, it feels warm, and of course, it hurts. But what is actually happening there at the cellular level? That, my friends, is the beautiful, complex magic of inflammation at work.
Right, so let's look at the proper textbook definition. The key word here, the one I want you to underline in your brains, is protective. Okay? This is the number one thing to remember. Inflammation itself is not the enemy. It's not a disease. It is your body's emergency response team, the ambulance, the fire brigade, all rushing to the site of an accident to protect you. And that's why we have to get this right. We have this idea that inflammation is bad, but without it, simple infections would become deadly. Wounds would just never heal. It is absolutely essential for our survival. Think of it as your body's own private army, always on guard.
This isn't some newfangled discovery, This is ancient wisdom. A Roman writer, Celsus, back in the 1st century, he described these 4 classic signs. Rubor, which is redness, tumor, the swelling, calor, the heat, and dolor, the pain. These are the 4 cardinal signs you will be looking for in your patients for the rest of your career.
Now, pay attention. For your exams, for your viva, for your own understanding, this slide, this is the master key. The entire complicated story of inflammation can be broken down into these 5 logical steps. We call them the 5 R's. First, recognition, then recruitment, after that, removal, then regulation, and finally, repair. If you remember this sequence, the whole chapter becomes easy. Okay, so let's start at the beginning with the first R, recognition. How does the body even know something is wrong? Who rings the alarm bell? Well, it has this incredibly sophisticated, built-in security system.
So stationed in all our tissues, we have these amazing security guards called sentinel cells. Your macrophages, dendritic cells, they're like watchtowers, constantly scanning the area. They have special sensors, like toll-like receptors, that are designed to spot trouble, either by detecting parts of microbes or by sensing signals from our own damaged cells. The moment they find an intruder, bam, they hit the alarm by releasing a flood of chemical signals called mediators.
All right, the alarm is blaring. So what happens next? It's time for our second R, recruitment. The body has to get its soldiers, the white blood cells or leukocytes, from the highway of the bloodstream to the actual site of battle in the tissues. It's time to call in the cavalry. Just look at this diagram. It shows the whole amazing journey. You see the leukocyte there, flowing along in the blood vessel? It can't just stop anywhere and jump out. No. It's a very elegant multi-step process. First, it has to slow down and start rolling along the wall. Then it has to stick on tight. And finally, it has to squeeze itself out. Let's break down how it does that. Okay, step 1. The blood is flowing fast, right? So first, the blood flow in that area slows down, and the heavy leukocytes get pushed to the edges of the vessel. That's called margination. Then they begin to tumble and roll along the surface, kind of like a ball rolling down a sticky slope. This rolling is possible because of some temporary sticky molecules called selectins. So after rolling along for a bit, the cell needs to come to a complete halt. That's where step 2, firm adhesion, comes in. Much stronger glue-like molecules, called integrins, get activated on the leukocyte. They lock onto the vessel wall like superglue. It's like throwing down a heavy anchor from a ship. The cell is now completely stopped, right at the exit it needs. And now for what I think is the most incredible part. This big, bulky leukocyte literally squeezes itself through the tiny microscopic gaps between the endothelial cells that line the blood vessel. It's absolutely amazing to watch. This process is called transmigration or diapedosis, and just like that, our soldier has left the bloodstream and has officially arrived on the battlefield. So, our troops have landed. They are at the site of injury. What is their mission? This brings us to the third R, removal. It's time for action, time to eliminate the enemy, whether it's invading bacteria or just cleaning up the debris from our own dead cells. And the main weapon of choice here is a process called phagocytosis. This literally just means cell eating. And our neutrophils and macrophages, they are professional eaters. It's a simple 3-step process. First, they recognize and grab onto the microbe. Second, they wrap around it and swallow it whole into a little bubble. And third, they just destroy it and digest it using a cocktail of powerful enzymes and reactive oxygen species. Enemy eliminated, job done.
ठीक है. So the battle is usually quick. But how the body manages the last 2 hours, regulation and repair, is absolutely critical. Regulation is the stop signal to call off the attack, and repair is, well, fixing the damage. Now, depending on how this whole story plays out, we get 2 major types of inflammation. If it's a short, sharp, successful battle, that's what we call acute inflammation. It's like a 100-meter sprint. But if the fight drags on and on, it becomes a long, exhausting marathon. And that is chronic inflammation.
This table shows the difference beautifully. Just look, acute inflammation is fast, starts in minutes. The main soldiers are neutrophils, and the damage is usually mild and resolves. Chronic, on the other hand, it's slow, takes days to develop. The main cells are different, macrophages and lymphocytes. And the big problem is the tissue injury is often severe and keeps getting worse. And you can see this difference with your own eyes under the microscope. Look on the left. You see all those tiny dots with the funny-shaped nuclei? Those are all neutrophils, a whole army of them. That's a classic picture of acute inflammation. Now look to the right. The picture is different, isn't it? You see those bigger cells with large, round, single nuclei? Those are your macrophages and lymphocytes. That's chronic inflammation. You must be able to spot this in your practicals. So, we've spent all this time talking about how inflammation is our friend, our protector. But what happens when it goes wrong? What happens when that fourth R, regulation, fails? Well, that's when this protective process becomes a dangerous double-edged sword. Our greatest ally can become our worst enemy. The trouble begins when the recognition system makes a mistake or the regulation system fails to switch off. In autoimmune diseases, our army starts attacking our own healthy cells. Friendly fire. In allergies, the whole system just goes crazy overreacting to something harmless, like dust or pollen. And in so many chronic diseases, like rheumatoid arthritis, it's that nonstop, marathon-style inflammation that just keeps damaging the joints, day after day. So let's end with this one thought. We absolutely need inflammation. It is the fire that cleanses infection and allows us to heal. But as doctors, much of your life will be spent dealing with the fallout from when this healing fire gets out of control and starts burning the whole house down. And learning how to control that fire, how to dampen it without putting it out completely, that, my dear students, is the true art of medicine. Think about it.
Namaste, students, and welcome back to our deep dive into pathology. In our last session, we saw the troops arriving at the site of injury. Well, today, we're going to witness the battle itself. We'll see how our body's cellular soldiers fight, how they communicate, and sometimes how they even make the ultimate sacrifice. It really is a microscopic war zone, and you, my friends, have a front row seat.
Okay, let's start with this. Just look at this incredible image. This is a macrophage, and I want you to think of it as a highly trained commando unit inside your body. It is on a relentless search and destroy mission, hunting down invaders like these little green bacteria you can see right here. I'm telling you, this is cellular warfare at its absolute finest.
So here is our battle plan for today. First, we'll look at our body's killer cells and how they operate. Then, we're going to see something truly dramatic, the neutrophils' death trap. After that, we'll decode the chemical messages they use to coordinate the attack and unravel the very powerful complement cascade. And finally, we'll see how the body calls a ceasefire and ends the war. So, pay close attention, huh? These are core concepts for you.
Right, our first section, our cellular soldiers, the leukocytes, have arrived on the battlefield. Now the real work begins, eliminating the enemy microbes and cleaning up all the debris of dead cells. And this process of, well, eating the enemy is called phagocytosis.
This whole process, phagocytosis, happens in 4 key steps. First up is recognition and attachment. The leukocyte has to identify the microbe, right? Then it has to grab on. The second step is engulfment, where the cell membrane just wraps around the microbe, pulling it completely inside. Third, this new little bag, which we call the phagosome, fuses with the lysosome, and that thing is just full of digestive enzymes. And finally, the fourth and final step, killing and destruction, all happening inside this new combined chamber, the phagolysosome.
So the enemy is trapped inside. Now what? How does the leukocyte actually kill it? Well, it has a very powerful 3-pronged arsenal. It uses chemical weapons called reactive oxygen species, a toxic gas called nitric oxide, and a nasty cocktail of deadly lysosomal enzymes. Let's start with that first one.
Reactive oxygen species, or ROS for short. Now, these are produced in a big chemical explosion called an oxidative burst. The most potent weapon in this arsenal, especially in neutrophils, is the H2O2 MPO halide system. Now, that sounds complicated, I know, but just think of it like this. The system essentially converts hydrogen peroxide into hypochlorite, which is basically the active ingredient in household bleach. It is the cell's ultimate bleach bomb, and it just obliterates microbes.
Moving on. You know, beyond just eating microbes, neutrophils have another, far more dramatic tactic. This is a process so fascinating it sounds like it's straight out of science fiction. We call it a neutrophil extracellular trap, or a net. Look here. On the left, you see nice, healthy neutrophils with their nuclei stained red. But look at the right. My God, the cells have ruptured. You see, in its final moments, the neutrophil literally commits suicide. It spews out its own nuclear material, all its DNA and proteins, to create this sticky, fibrous web. It is a Spider-Man-style last resort to trap the enemy. And here you can see the result. Look at those bacteria, hopelessly tangled in that web of chromatin from a dead neutrophil. This net, it doesn't just physically trap the microbes and stop them from spreading, it's also loaded with antimicrobial proteins that kill the captured pathogens right there. A truly heroic sacrifice. Now, no army can fight effectively without communication, right? In the battlefield of inflammation, this communication happens through chemical messengers that we call inflammatory mediators. These are the signals that call for backup, direct the troop movement, and even give the final order to attack.
Okay, now this table might look a bit overwhelming, but don't worry, just think of it as your cheat sheet for the key players in this whole drama. You see names like histamine, which opens up the blood vessels, prostaglandins, which are responsible for pain and fever, and cytokines, which are the master regulators. We'll touch upon a few of these in a little more detail now. Let's talk about those prostaglandins. They're made by an enzyme called cyclooxygenase, or COX. And this, my friends, is clinically very, very important. You see, there are two forms. COX-1 is the housekeeper. It's always on, doing good things like protecting your stomach lining. COX-2, on the other hand, is the fire alarm. It only gets switched on during inflammation. This is why drugs like aspirin can cause stomach issues. They block both the bad fire alarm, COX-2, and the good housekeeper, COX-1.
Now, among the most powerful messengers are the cytokines, especially two you must remember: tumor necrosis factor, or TNF, and interleukin-1, or IL-1. If this whole inflammation thing is an army, then TNF and IL-1 are the generals. They are produced mainly by macrophages, and they direct the entire response, telling all the other cells what to do and when.
So what exactly do these generals do? Well, first, they order the cells lining the blood vessels to become sticky, so that leukocytes can grab on. Second, they activate the leukocytes themselves, getting them all pumped up and battle-ready. And third, they are responsible for the systemic effects you actually feel during an infection, like getting a fever. And in chronic diseases, TNF can also cause something called cachexia, which is a very severe weight loss.
All right, let's move on to one of the most elegant and powerful systems in our entire body's defense, the complement system. It's a series of about 20 proteins that are just circulating silently in our blood plasma, just waiting for a trigger. And when they get activated, they set off a very rapid and very powerful chain reaction, or a cascade. There are three main ways to kickstart this cascade. The classical pathway, which is triggered by antibodies, the alternative pathway, which is triggered directly by the microbe itself, and the lectin pathway, which recognizes microbial sugars. But here's the crucial point, okay? It doesn't matter how it starts. All three of these pathways, they all converge on one single critical step, splitting a protein called C3. And once that C3 protein is split, it unleashes three major defensive functions. First, little fragments like C3a and C5a act as inflammatory signals, calling in even more soldiers. Second, the C3b fragment acts as what we call an opsonin. Basically, it tags the microbe screaming, "Eat me!" to all the phagocytes. And third, the cascade ends by forming the membrane attack complex, or MAC. This thing is like a drill that punches holes directly into the microbe, causing it to just burst and die. A devastatingly effective system.
Every war, even one happening inside our own bodies, must eventually come to an end. You see, the inflammatory response is designed to be short-lived,
But its weapons are so powerful that if you leave it unchecked, it can cause significant damage to our own tissues. This is the real double-edged sword of inflammation.
And this captures the dark side of it perfectly. Sometimes you get collateral damage. Healthy tissue gets hurt during a long, prolonged fight against a tough microbe, like in tuberculosis. Other times it's a case of friendly fire. When the immune system gets confused and wrongly attacks our own body, this is what leads to autoimmune diseases. And sometimes it's just a complete and total overreaction to something totally harmless, which is exactly what we see in allergies.
So how does the body call a truce? Well, it's an active process. The inflammatory mediators, they have very short half-lives, so they just disappear quickly. The body also starts actively producing anti-inflammatory molecules, like liposins, and special cytokines like TGF-beta and IL-10. These are the signals that actively suppress the inflammation and begin the process of healing.
Which brings us to our final and most crucial question. After everything we have seen today, is inflammation a hero or is it a villain? We have seen it as a sophisticated, life-saving defense mechanism, a hero that protects us from infection. But we have also seen its potential for destruction, a villain that can cause chronic disease and so much suffering. So what is it, hero or villain? The truth is, it's both. And understanding this duality, that is the key to mastering pathology. Think about that. We will see you in the next class.
Hello, Baccho, and a very warm welcome to all of you. Chalo, let's get started. We're continuing our journey into pathology, and today we're hitting part 3 of inflammation and repair. We've seen the first attack, right? The acute response. But what happens after the dust settles? Let's find out. Just look at this picture. I want you to really see it. What do you think is happening here? This is a heart that is so inflamed, its surface is literally covered in this rough, shaggy coat. This, my friends, is fibrinous pericarditis. And it has this classic bread and butter look. You know, like if you took 2 slices of buttered bread, pushed them together, and then pulled them apart, that's the texture. It's a pretty dramatic result of acute inflammation. But the real question is, what comes next? So here's our game plan for today. First, we'll look at what happens right after that initial battle. Then, we'll see what happens when the fight just doesn't end and it turns chronic. We'll meet the special forces of the body, the cells of this long war. We'll check out the body's amazing strategy of building these biological fortresses called granulomas. We'll then look at the system-wide alarms, and finally, how the body tries to repair the battlefield. Pay attention, this is a very, very important topic for your exams. Okay then, so the first responders are neutrophils. They've come in, they've fought hard, but the story isn't over. Not by a long shot. The aftermath of acute inflammation. This is where things get really crucial. It's a major turning point. Now, one of the, messier outcomes is something called an abscess. Just think of it like a walled-off battle zone. When the body can't completely get rid of the enemy, and we're usually talking about those pus-producing or pyogenic bacteria, it does the next best thing. It builds a wall around them. It creates this pocket filled with pus, which is really just a horrible soup of dead neutrophils, liquefied tissue, and the bacteria themselves. It's the body's desperate attempt to contain a really nasty situation. And this slide, it shows it perfectly. On the left, that's the big picture, a gross specimen of a lung, and you can see it's just filled with these pockets of pus. Those are the abscesses. Now, let's zoom in. Look to the right, under the microscope. See that huge, dense, dark purple area right in the middle? That, my friends, is the abscess cavity. It's absolutely stuffed with neutrophils and cellular junk, and it's surrounded by all this inflamed lung tissue. From the macro view to the micro view, this is what an abscess is. So after any acute inflammation, the body basically comes to a fork in the road. There are 3 possible paths it can take. Path number 1, the best case scenario. Complete resolution. The body cleans up the mess, the damaged cells grow back, and the tissue is good as new. Perfect. But if the damage was too bad, if the structure is destroyed, then you get path number 2, healing by scarring. The body patches up the hole, but it's not the same. And the third possibility? The enemy just won't give up. The battle rages on, and the acute inflammation slowly turns into a long, drawn-out war. And that is chronic inflammation. Which brings us right to our next big topic. What happens when that initial sprint of acute inflammation becomes a grueling, never-ending marathon? This is chronic inflammation. It's a slow, simmering conflict that can last for weeks, months, or even for the rest of a person's life.
So the textbook definition is very clear. It's a long-lasting response where three things are happening all at the same time. You've got ongoing inflammation, you've got continuous tissue injury, and you have the body constantly trying to repair itself. It's a messy, chaotic cycle of destruction and healing all happening at once.
Now this is a fantastic comparison. On the left, that's acute inflammation in the lung. See those little air sacs, the alveoli? They're packed with tiny dots. Those are your neutrophils, the foot soldiers of the acute response. Now look to the right, chronic inflammation. It's a completely different world, isn't it? The soldiers have changed. Instead of neutrophils, you see these bigger, rounder cells, lymphocytes and macrophages. And just look at the damage. The lung architecture itself is being destroyed. This isn't a quick fight. This is a long, destructive siege. So why does this even happen? Well, there are three main culprits. First, you've got persistent infections. Think of bugs like the tuberculosis bacillus. They are experts at hiding from the immune system. Second, you have hypersensitivity diseases, autoimmune conditions like rheumatoid arthritis, where the body's immune system gets confused and starts attacking itself. And third, there's prolonged exposure to toxic stuff, like silica dust for a mine worker, that the body just can't get rid of.
You see, if neutrophils are the frontline infantry who rush in first, then chronic inflammation is when the body calls in its special forces. These are the commandos, the strategists, the soldiers built for the long haul, the macrophages and the lymphocytes.
Now, the macrophage is an absolutely fascinating cell. It's got a split personality. It can be activated in two main ways. The first is the classical pathway, which creates the M1 macrophage. This is the warrior. Its job is simple: destroy the enemy. It's pro-inflammatory and it kills microbes. But then you have the alternative pathway, creating the M2 macrophage. This is the repair crew. Its job is to calm things down, clean up the debris, and start rebuilding. The balance between this warrior and this repairman is absolutely critical. And here's the thing, macrophages don't work alone. They have a very, very close relationship with T lymphocytes. It's a feedback loop. The macrophage shows a piece of the enemy to a T cell. The T cell gets all fired up and releases signals that, guess what, activate even more macrophages. So they keep hyping each other up, right? This creates this self-sustaining cycle that keeps the inflammation going and going. But sometimes even these special forces can't win the war. The enemy is just too tough. So the body does something incredible. It resorts to Plan B. If you can't kill it, jail it. It builds a biological fortress to wall off the threat. And this fortress is called a granuloma. So what is a granuloma? It's a very specific pattern of chronic inflammation. At its heart, it's just an organized collection of these activated macrophages. But they look different here. They become all plump and pink, and they start to clump together, almost looking like skin cells, epithelial cells. That's why we call them epithelioid cells. And usually, they're surrounded by a ring of lymphocytes, standing guard.
And here it is. This is the textbook example of a granuloma, taken from a patient with tuberculosis. You have to know this slide. Look closely. Right in the middle, you've got that pink, crumbly, dead tissue. That's caseous necrosis. Caseous means cheese-like. Surrounding that are the epithelioid macrophages. And you see those massive cells with lots of nuclei arranged like a horseshoe? Those are Langhans giant cells. They're formed when many macrophages fuse together. And finally, the whole thing is wrapped in a cuff of dark lymphocytes. It's a beautiful, deadly structure.
But Joe, this table is extremely high yield. I want you to take a mental picture or a real one. When you see a granuloma under the microscope, your list of possible diseases becomes very, very short. Is it tuberculosis with that cheesy center? Is it sarcoidosis, which usually doesn't have necrosis? Or maybe it's Crohn's disease in the gut? Knowing these associations is absolutely vital for your exams and for your clinical practice. Now, inflammation is rarely a purely local event. Think about it. When there's a serious fire in one neighborhood, it doesn't just involve the local fire station, right? It rings a national alarm. The same thing happens in the body. A big local fight can trigger system-wide alerts that affect everything. And these systemic effects, we call them the acute phase response. You know them well. First, you get a fever. That's just cytokines telling the thermostat in your brain to crank up the heat. Second, leukocytosis, a high white blood cell count, as the bone marrow starts pumping out more soldiers. And third, the liver starts churning out these acute phase proteins. And this is why we order a CRP blood test, Bacho. C-reactive protein is one of these.
And when it's high, it's a direct signal from the body screaming, there's inflammation somewhere. All right, the battle is over, or at least it's been contained. What now? Well, now the body has to clean up and repair all the damage. We're now entering the final phase, tissue repair. It's time to heal the battlefield. Just like before, there are two main ways this can go. The perfect outcome is regeneration. The damaged tissue is completely replaced by new, healthy tissue, and everything goes back to normal. The liver is the poster child for this. The other path is scar formation, or fibrosis. This is what happens when the tissue just can't grow back. The body fills the gap with connective tissue, basically collagen. It provides support, it plugs the hole, but it doesn't do the job of the original tissue. A heart attack, for example, always heals with a scar. And the ability to regenerate all comes down to the type of tissue. We basically put tissues into three groups. First, labile tissues. Think of your skin or the lining of your gut. They're constantly dividing, so they have a great capacity to regenerate. Second, stable tissues, like the liver or kidneys. They're normally quiet, just doing their job, but if they get injured, they can wake up and start dividing. And finally, permanent tissues. Your neurons, your heart muscle cells. Once they're dead, they are gone forever. Repair for them is only by scarring. You all know the Greek myth of Prometheus, right? Where his liver was eaten by an eagle every day, only to grow back every night? Well, our textbook puts it beautifully. The reality, although less dramatic, is still quite impressive. The liver's ability to regenerate itself is truly one of the marvels of the human body. It's a perfect example of what stable tissues can do. And that leaves us with one final big question, a question for your generation of doctors to solve. We know the heart, a permanent tissue, heals by scarring. We know the liver, a stable tissue, can regenerate. So the ultimate challenge is this. If we truly understand what tells a tissue to regenerate versus what tells it to scar, could we one day switch the signals? Could we convince a damaged heart to stop scarring and start regenerating itself, just like a liver? Think about that. Thank you, and I'll see you in the next class. Hello, class. So, have you ever really thought about what's happening when your body heals from a cut? It's not just magic, you know? It's like a highly organized, very efficient construction project. Today, we're going to go behind the scenes. We'll be the foreman on this construction site, watching how the body masterfully repairs itself. It's a really fascinating process, and understanding it is crucial for you. So, let's start with a basic question. When you get a deep cut, how does it actually heal? Does the body manage a perfect brand new replacement? Or is it more like a quick patch-up job, a bit of jagad to get things working again? This is a fundamental question, and it gets to the very heart of tissue repair. Basically, the body has two main strategies up its sleeve. On one hand, you have regeneration. This is the ideal situation, a perfect restoration. The tissue becomes as good as new, ekdom original. But more often than not, the body goes for scarring. Think of this as a functional patch. The damaged tissue gets replaced by connective tissue. It's not the same as the original, but it's strong and it gets the job done. It patches the hole. So when that perfect regeneration isn't possible, the body has no choice but to form a scar. And this kicks off a full-on construction project. Let's take a look at the blueprint, shall we? How exactly is a scar built? You know, what's really amazing is just how organized this whole project is. It happens in three very clear phases. First up, inflammation. This is the cleanup crew. They arrive to clear out all the debris, dead cells, and any microbes. Then comes proliferation. This is where the real construction begins. We get new blood vessels, and a temporary framework called granulation tissue is laid down. And finally, remodeling. This temporary frame gets replaced by strong collagen, and the scar matures. So remember, clean up, build, remodel. Simple, no? Let's focus on this term for a second. Granulation tissue. Very important for your exams. Huh? What is it? Well, it's that temporary scaffolding. If you've ever seen a healing wound, it has that soft, pink, bumpy look. That's granulation tissue. And why does it look like that? Because it's packed full of new capillaries, fibroblasts, and inflammatory cells. It is the busy, bustling work site of our construction project. And here, look at this. This slide gives us a peek at that bustling worksite under a microscope. See all those red structures? Those are newly formed blood vessels, the supply lines, bringing in all the oxygen and nutrients. You can really get a sense of how active and busy this phase of healing is. Now, let's see the finished product. Look here. That once busy worksite has completely transformed. The blue stain on this slide is highlighting the dense bundles of collagen. The new blood vessels? They're mostly gone. This is a mature, strong, avascular scar. The construction is finished, and the site has become quiet. Okay, so we've seen the blueprint.
But who are the workers on this site, and how do they talk to each other? How do they coordinate? Let's meet the repair crew and understand their signals. At the absolute heart of this whole project is the macrophage. You can think of it as the site supervisor. This guy does everything. It clears away debris, it releases chemical signals to get other cells working, and it calls in the fibroblasts, the masons, to start building. And to be a bit more specific, it's the M2 or repair mode macrophage that's in charge here. Remember that. Now, you know every construction site needs supply roads, right, to bring in all the materials. In the body, this process of building new blood vessels is called angiogenesis. And a key signal that gives the green light for this is something called VEGF, vascular endothelial growth factor, a very, very important molecule. Now, if there is one master signal you must remember from all this, it's this one, TGF-beta, transforming growth factor beta. This is the molecule that basically shouts to the fibroblasts, okay, boys, start producing and laying down the collagen. It is the key signal for making the scar tissue, a process we call fibrosis. Absolutely critical. So, now that we have the blueprint and we know the workers, let's see how it all plays out in the real world, in the clinic. We'll look at two classic examples of healing that you will see all the time, healing by first intention versus second intention. Okay, look here. First intention is for a clean surgical cut. The edges are neat, the gap is small. It's a simple, fast process with minimal scarring. But second intention, this is for a large, irregular wound. Think of a big ulcer or an abscess. There's a big defect, lots of inflammation, and much more granulation tissue is needed. It's a much bigger, much messier construction job that results in a more significant scar. And this timeline for first intention really shows you the process beautifully. Within 24 hours, neutrophils are on the scene. By day 3, macrophages take over and granulation starts. Day 5, you get peak new vessel formation. And by about day 30, you have a complete avascular scar. It's a beautifully organized sequence of events. But, of course, things don't always go according to plan. So what happens when the construction project goes wrong? When there are delays, or bad materials are used, or when the workers just keep building and building without stopping? Now, this slide is very, very important for all of you. The road to healing has many potential roadblocks. Infection is a major one. It keeps the inflammation phase going for far too long. Conditions like diabetes can mess with blood flow. Poor nutrition? All right. If there's no protein or vitamin C, where will the raw materials for the construction project come from? Even some medications, like steroids, can slow the whole thing down. These factors are critical to know. For example, just look at these pictures of chronic wounds. On the left, you see a venous ulcer. Here, the blood can't drain away properly. It's a drainage problem. On the right, an arterial ulcer. Here, blood can't get to the tissue. It's a supply problem. And in both cases, the result is a wound that just refuses to heal. And, sometimes the problem isn't too little healing, but too much. The construction crew goes completely overboard. This can lead to a hypertrophic scar, which is raised but stays within the wound's boundary. But if the scar tissue grows beyond the original wound boundary, like it's trying to take over the neighborhood, and it doesn't go away, that is a keloid. And it's really important for you to recognize that keloids can look very different depending on a person's skin tone. In lighter skin, they might appear as these raised red scars, but in darker skin, they can form these large hyperpigmented growths. The underlying process, that overproduction of collagen, is the same, but the visual presentation can vary quite a lot. Okay, Cello, let's summarize the key takeaways. First, healing is always a balance between a perfect fix and a practical patch job. Second, scar formation is a clear 3-step process: inflammation, proliferation, and remodeling. Third, the macrophage is the site supervisor, and TGF-beta is the master signal for making the scar. And finally, healing can be neat, first intention, or messy, second intention, and lots of factors can mess it up. So I want to leave you with this final thought. The body's repair process is such a delicate balance, isn't it? Now that you understand the blueprints, the workers, and the signals, it makes you think, as a future doctor, how can you help tip the scales? How can you help your patients achieve better, more perfect healing? That is one of the great challenges in medicine, and it's a real testament to the incredible resilience of our bodies.